typical gas lift design and troubleshooting. So the outline is we will have an introduction. Introduction will be a video, and then we're going to review the actually design and do the design using Casper for the continuous gas lift design. As you know, we have two types of gas lift design: intermittent and continuous. So the focus will be on continuous gas lift design. And finally, we are going to have a troubleshooting for a gas lift well. And then this will be, these two actually parts all will be done using Prospect.
For the customer. During the initial unloading process, casing and tubing pressure gradients in the static loaded condition are equal. All gas lift valves are in the open position from the weight of the hydrostatic fluid in the tubing and casing annulus. As gas is injected down the casing annulus, it displaces the kill fluid through the opened gas lift valves into the tubing string and to the separator or storage tank. As the lift gas continues to displace and unload the fluid in the annulus, the pressure on the casing will continue to increase, maximizing the artificial lift capability. When the annulus fluid is unloaded to the first valve depth, the casing pressure will have reached its designed kickoff pressure, in this case 800 psi. This pressure is sufficient to lower the casing fluid below the first mandrel and allow gas injection into the top valve. This injected gas causes a lighter gradient in the tubing, allowing the well to unload the kill fluid entering the tubing string from the lower valves as the well continues to unload. Once the annular fluid is displaced to the second valve depth, injection gas begins entering the tubing from the second valve. The combined injection of the first and second valves exceeds the throughput of the surface input choke, resulting in a casing pressure decline. This decline causes the top valve to close. Injection continues from the second valve as the well continues to unload, lifting both the displaced kill fluid and produced well fluids. Note that as the well is unloaded to the second valve, the pressure at the bottom of the tubing is less than the static bottom hole pressure of the reservoir. This differential, known as drawdown, causes reservoir fluids to flow into the wellbore. The same process is repeated every time the fluid in the casing is unloaded down below an additional valve, allowing the upper valve to close as the unloading process continues and the well is unloaded to its deepest point of injection. A pressure recorder installed at surface will record a casing pressure drop each time a valve closes. Reading of the recorded pressure as the well unloads will give an indication of the valve operating depth.
Okay, so this was somehow introduction of how the gas lift actually operate and how unloading will be conducted for a continuous gas lift well. Okay, so this is the design for a gas lift using Prosper. So what would be the objective is to find the maximum production rate achievable using gas lift. And then we need to know the depth and injection rate for the optimum gas lift, and then also design the operating and unloading valve. Okay, so what would be the procedure is to set up the gas lift design parameters, calculate the design production and gas injection rate, space out the valve, determine the valve trim size and dome pressure, and calculate the production sensitivities using the gas lift design. Okay, so this is the procedures. What we have for the continuous gas lift is to go for the options, change actually the natural oil well to continuous one to gas lift well. And then the second important part is to actually change the PVTs if there is any properties of the gas. We need to include that. and then also go for the IPR and change the required one accordingly. And then we do the outcome will be our performance curve, which is done through our condition, the gas lift design condition. And then we will do the design. And then in order to come up with the dome and test rack opening pressure, we need to do some calculation. And then after all this calculation have been done, we need to transfer all this valve depth, and then we do a system calculation. So these are the procedure that we will do through the Prosper gas lift design using Prosper. So in this case, I hope you can going to do is that we are going to base our course on actually existing tutorial. So what we're gonna do is that we are going to open actually. So from the sample, I hope all of you can access the samples, and from the samples you choose Prosper, and Prosper the tutorial number 20. Okay, so in tutorial number 20, we created actually an oil well design is created, and then this well was matched against well test data. So that's why in this match we are going to open this case. Okay, open. Okay, so please do so. Open case number 20, and then because test number 20 will be our basis, and from this case number 20, what we are going to change is that this well is already actually produced for some time. Okay, and then the reservoir pressure is now dropped from 3,500 to 3,000 psig, and also the water cut is changed from 0% to 80%. So that's why we are going to make a difficulty for this well to produce. So that's why the actually having an artificial lift will be actually an important for this case to be done. So that's why in this case we are going to do the gas lift design. So change the parameters, and then equipment data and all the important variables will be changed accordingly. So this is a step by step actually procedure. So we are going to define the options. So make sure to access the options. So here in this case, what you can see is the properties of the you can access all the Prosper actually input data and analysis by using this menu bar, or using this rectangular actually spaces available here. As you can see, for the left one, we can have the options for actually option summary, and then PVT. If you want to access this PVT, just double click on this, and then you can have the PVT. For the IPR, just double click, and then you can have it. And also you can access all the information or data through the menu. So in this case, we are going to go for the options and click on options. Okay, so here in this case, as you know, this is an oil well, a natural oil well, and then this natural oil well was already actually verified and validated by well test data. In this case, in the option, the first step is to change the well to or include some artificial lift method for this well. In this case, we are going to choose the continuous, gas lift continuous, and then the type would be no friction loss in animal. So this is the only thing that we are going to change for the software. So all of you done this? Have you done this? Okay, so great. So click on done. So in this case, you are already included, or introduce gas lift continues to your well. So the second step is to include the PVT, or describe the gas lift PVT. So in order to do that, we need to go for the system, okay, and then click on the gas lift data. So in this case, we are going to include the gravity of the gas lift. So the gravity that we are going to include is 0.8. So this is the only change that we are going to include, and then make sure that the valve depths are specified is because in this case we are going to design the gas lift, and then this design will give us the actually depth for each valve, and then the depth, all the information or the details will be transferred to this. So we are not going to change any of this right side of this actually window. The only thing we are going to change is to include the gravity of the gas lift gas, and then change the gas lift method to be valve depth specified. So click on the done, and let's move on to the next section. Okay. Okay, so for this case, we are going to change the IPR. For changing the IPR, as you can see here, we can go for the system, okay, for this menu, and then go for the inflow properties, or we can double click on this window, okay. Okay, in this case, what we are going to change is that reservoir pressure here, it will be changed, and water cut also will be changed accordingly. So the reservoir pressure will be changed to, will be decreased. So will be decreased to 4,000, and then the water cut also will be increased to 80%. But before that, let's actually plot our IPR and see what is actually the case. As you can see from the IPR plot, our absolute flow potential and the PI is already included. So this is the original case. So, and then if we change this to 3,000, so the well already produced for quite some time, and then the water is already also increased to 80%, and then we are going to click on the calculate. So remember, every time you do the changes for the IPR data, you need to let the software know that these changes are already incorporated. So that's, you need to click on the calculate, okay? Then when you click on the calculate, the plot will be shown. As you can see, the absolute flow potential is changed to this number, and then formation PI is still, and the skin also will be changed, and the information that are included for this well are shown on your right side. So are you done with this step? So you all change the pressure and also water cut. Okay, finish. What I'm going to do is that I'm going to refer to one of you. Can you change it to 4,000?
Oh, yeah, sure.
Okay, 4,000, and then 0. Water cut. Okay, great. So this is 23,223, and then the formation PI is 10, and the skin is 2. Okay, so remember these two. Let's remember the PI, and then let's move on to the other part. So change the reservoir pressure. The cut 80%, great. And then calculate, great. Okay, good. So you can see that we have changed. Actually, the absolute open flow potential is changed, but the PI was changed, right, or not?
Yeah, I think it's kind of remain. It's now this around 10. Yeah, it's kind of remain. Just the ROF change.
So do it again. Okay, there are actually slight changes in the formation PI, but all of you know that the PI is related to the Q and delta P. In this case, the top, no, from the top. Okay, so the design rate method will be based on the maximum production. Okay?
All right.
So calculated from the maximum production. So the maximum production will be 30,000. 30,000, okay, and then maximum liquid rate 30,000, maximum gas available 10 million, and maximum gas available during unloading 10 million. Flowing top node pressure will be 200, unload top node pressure 200, operating injection pressure 1,500, kickoff injection pressure 1,500, desired DP across valve 50, change it to 50. Maximum depth of gas lift 7,500. Water cut 80%. Maximum valve spacing 250. The static gradient of kill fluid will be 0.46 psi per foot. Minimum transfer DP 25%. Maximum port side. This will be done later. So the safety for the closure of the last unloading valve is 0. Total GOR is 400. The rating percentage will be 100. Valve type will be casing sensitive. Okay, make sure to include casing sensitive for this one. Okay, and okay, all this injection point will be injection point is an orifice. Okay, and then minimum CHP will be 50, and then we are going to check yes. Dome pressure correction about 1,200. Yes, this is yes. And check rate conformance with IPR. Yes. Petroleum expert 2 will be used. Bexambril for pipe correction. IPR for unloading. Yes. Orifice size will be calculated DP based on at the orifice. The rating percentage for the orifice will be 100. And then valve size selection. Okay. For valve size selection, you are going to go for the COMCO.
Oh, so what is that?
Yeah, in the current valve type, in the right, you are going to choose COMCO. Okay, from the COMCO, you are going to use R20 normal. Okay, no need to change to select, because then later we are going to actually give it value. So when we include this, we are going to select the continue. Okay, so wait, please wait. Okay, no way. Okay, okay. All of you have done, right? Don't do anything, Sheng. So let me just come back to all of you. So all of you have done all these steps.
Yes,
No.
doctor.
Okay, so get the rate, you already click on the get rate, right? And then you are going to, after getting actually the rate, and then you are going to have a plot. Please click on the plot. Okay, so can you describe, I'm going to, what would be the vertical, what is the vertical axis and the horizontal axis are shown, or can you start with the data from the vertical axis and horizontal axis?
The vertical axis demonstrates the oil production.
Okay.
The x-axis illustrates gas injection.
Gas injected. So as you can see, the maximum gas injection is 13 or 14 million scarf, starting from 0 to 14. And then, as you can see, the vertical axis is our oil production rate, which is start from 0 to about 1,600. So as you can see, from the 0 to about 7 million or 8 million, we will have actually the production increase, but after that there will be a decrease in the production, so we will have some gas locking in our system. So in this case, the optimum production rate would be somehow to be about 6 million will be. So this is somehow a description fact that can be derived from this picture, that what would be the best or the optimum production or the gas lift gas for your case or for your production. Okay, so I hope all of you reached to this step and understand what the performance curve means. If you go back to our presentation, we have gas lift design condition and we have our performance curve. I've already included that. Okay, in this case, what we are going to do is that we are going to perform the gas lift design. So after we've already done with the performance curve, we are going for the gas lift design. So what we are going to do is we are going to exit. So please click on the finish. Okay, so the top part is already done. Okay, now we are going to the below part, which is the design. Okay, so we are going to click on the design. Okay, so as you can see, the design will be done, and then okay, we already done the design. Okay, and then after we've done the design, we can visualize actually the plot. Okay, okay. So this is the visualization of the plot. So I want one maybe in your, but I think the majority of you already understand this case, because this is one of the integral part of your production engineering course. Okay, but here we are going to understand, instead of other cases, we are going to understand how this works. That's why I've included the video. Is that this is a very important, as you can see in this case, clearly the location of the valves are included, and then the closing pressure, the opening pressure, this is the opening pressure and this is the closing pressure for each valve is included. The main valve, which is the gas injection will be done through, is the orifice, already included. What we can understand is that when the casing pressure, here in this case, the casing pressure is higher than the tubing pressure. So that means that there will be actually a flow. So this is the first actually inference. So the casing pressure curve is in the orifice location is higher than the tubing pressure. So this means that the gas is already flowing into the tubing. The second one is the curve of our tubing. As you can see, actually the initial case is 2,124. So that means that there is a drawdown in our case from 3,000 to 2,124. So that means that this is a drawdown, and there will be, if you minus 3,000 from 2,124, so there will be a drawdown. So this is the second indication. But what makes this actually plot important is the P minimum and the P maximum. So this triangle, can you show this, Sheng? The triangle, the green triangle and the yellow triangles. Okay, these are very important. The green triangle, you can, maybe it cannot be seen from this. There is this green triangle is our minimum pressure, and this yellow triangle is our maximum pressure. So this is very important to actually understand what are this P minimum and P maximum represent. So listen carefully. So in the gas lift design, P minimum represents the minimum pressure drop that can be achieved at the specific depth in a well during the unloading process when the gas is injected at the defined depth. The pressure drop occurs when gas is injected into the wellbore, which reduces the hydrostatic pressure of the liquid column and helps lift the liquid to the surface. P minimum is important because it helps engineers determine the minimum gas pressure needed to lift the liquid at that depth. On the other hand, P maximum, which is shown in the yellow triangle, represent the maximum pressure drop that can be achieved at the specific depth in the well during the unloading process. So this pressure drop occurs when gas lift valve are open and closed. As one valve closes, for example, you look for gas lift number one. As this valve is closed, there is momentary maximum pressure drop at the valve as the one below is opens. So this is a very small moment that one valve, the top valve is closed, and the minimum, the below valve is opened. So this drop in pressure helps lift the liquid to the surface. So P max is important because it helps engineer determine the maximum gas pressure needed to achieve the desired production rate while avoiding excessive gas breakout. So in both cases, P minimum and P maximum are important design parameters in gas lift system because they help engineers determine the optimum gas injection rate and pressure to maximize well productivity. So by analyzing these two pressures at different depths, you can determine the most effective configuration for gas lift valve to ensure that the gas injection rate is optimized for each depth. So this is the case for our maximum P minimum and P maximum. So let's move to the next. We can finish, click on the finish, and then we can go for the results. Okay, so the results. So what you can see, don't click on anything now. What you can see here is that, as I said to you before, we need to actually come to, or we need to do the, calculate after finishing the gas lift design, we need to calculate the pressure. These two pressures are very important: the dome pressure and also the test rack opening pressure. So this is very important. That's why we need to do the calculation. So in this case, we are going to click on the calculate. Please click on the calculate. So after clicking on the calculate, the dome pressure and the test rack pressure will be determined. Okay. So this determination actually makes it, one of the important steps in order to do the next step. So so in this case, what you can do is click on the done. click on OK, done, and then OK, done. Or you can go for done and then another time done. Okay, so in this case, double click on the PVT, please, and this, yeah, PVT. Click done. Okay, so you go for, don't do anything. You go for the system. Okay, gas lift data. Okay, and then choose the valve depth specified. So you see here, in order to continue for our case, we need to transfer all the design to this page. Okay, in order to do that, please click on the transfer. Yes. And then, yes, from gas lift design, exactly. From new gas lift design. Remember, we've done the new, right? Okay, done. Okay, as you can see, actually the already actually we've actually finished all this, and then as you can see we have three gas lifts. Ida, that's correct, right? How many gas lift valve we have? Ida?
We have 4, including the main one, which is the orifice.
Okay. The right answer is that we are not considering the orifice, which is the below, the most below valve. We are not consider this as a, unloading. So we have 3 unloading valve and 1 orifice, which is our injection or operating point. Okay. So this is always operating. So it's not going to be closed. So this is our orifice, the size of the orifice that next will be determined. So we have 3 gas lift valve and 1 operating orifice, which is located at depth of 6,296 feet. Okay, so this is our actually design in order to actually for to do more actually calculation. What we are going to do is that we are using this 6,296. So please make it, click on this, Shane. 6,290, the operating, yeah. Copy it. Okay, and then change it from, fixed depths. The gas lift method will be fixed depth of injection. So we are considering, and paste it here, we are considering that the unloading is already done and the well is already producing. So that's why the only operating point is our orifice, which is located at depth of 6,296. So after we've done this, actually we will, select the done and select done, and then this is actually complete our gas lift design. So the gas lift design is already done. So if I refer to the presentation, we need to do a system calculation here. Okay, for the system calculation, remember all the calculations will be done through our, yes, this is the calculation. You need to access the calculation. So system, the second option. Okay, 3 variables. Okay. So here you need to specify the variables, and you see the top node pressure, same. You can make it do 250, but the water cut is 80%, right? And the total GOR is 400. Okay, we are going to actually, all of you done, right? So you change these 3 input data, and then don't change any of the below. Our surface equipment, Bexambril, vertical lift, PE2. Our solution node will be the bottom node. and then rate is automatic linear, and then the left hand intersection will be this allow. So okay, so you can click on continue. Okay, and then reset all. You just variable one or reset, and then choose the gas gas injection gas lift gas injection rate. Okay, so the case here is that I want to include 0 to 10, and then 0 to 10 is to, and then the distance between 0 and then the interval will be 0.5. What can I do actually is that can you go for generate? Click on the generate. Okay, so click on steps. Okay, the first value is 0. The number is 10, and then increment 0.5. Generate. Okay, so as you can see, this is easily generated. No need to type anymore. So in this case, you go for the generate, and then steps, include the steps, and done. So you can continue. Click on continue. Okay, and then do calculation, right? And then plot, system plot. Okay, so great. So as you can see, this shows actually different gas injection rate, and then our IPR, and then this is clearly indicated that when you don't have gas, there will be no actually production, because there will be no intersection. Increasing the gas lift actually gas is contributed to the increase of production, as you can see, from 0 to 10. Okay, so any question about this plot? Okay, great. So click on finish, please. And then click on the sensitivity. So this actually slide showing you the sensitivity, but I want to have the oil rate, the oil rate instead of the pressure in this plot. No. Okay. You can go for the variables. Okay. And then yes, oil rate. Okay, great. So as you can see here, okay, what I want, Sheng, is to also change the horizontal variables values from 0 to 10. This information through this, and then as you can see, the injection depth is 6,200. Actually 96, our determined injection for our case. So that will be somehow actually concluding our so you can click on yes. Done. Okay, you can go for straight for the main. Okay, great. So these are some steps, actually preliminary steps, in order to do a design for your gas lift. There are main component in our considerations. As I said, actually the depth for unloading valve, description of your minimum pressure, P minimum and P maximum, that are actually very important in determination of your gas injection rate, and other things that I think I'm going to share with you this video in order to actually do for others like Daha and Abdurrahman and others that have not been actually prepared or there was no time for them to do that. So they can use actually the video in order to redo the examples. But remember, there will be some questions that might be actually used for your test 2 or final from understanding of this case. So that's why this is the design. I think I'm going to just open the Q&A sessions for all of you in order to ask if you have anything that you might ask or you have any question that can. So Ali Hassan, are you there? Ali Hassan, can you hear me? Ali Hassan. Okay. Bhavin, are you there?
Yes, doctor.
Okay, Bhavin. So is this your first case using Prosper for gas lift?
Yeah, it's my first time using.
Full gas lift gas volume. We need to find the injection point that can actually satisfy our requirement, which is injection of that amount or pre-specified gas to the well. So what are the dependents actually? So we are talking about analyzing the well test and then finding the injection point. So these are related to the 4 important variables. So that's why these 4 important variables are fluid response, so the PVT, and then reservoir pressure, the IPR data, tubing response, and the valve response. So these 4 variables are, in gas lifted well are very important to play with. So that's why in order to incorporate all these 4 variables, a quick actually, specific actually solution is actually found out in the Prosper, which is quick actually that will be done for the gas lift, and then we will see the effect of these 4 parameters to find the best answer. So the procedure is to we have a Prosper file. We are going to review it, and then we are going to enter the well test data and then also the gas lift data, and then this is the quick look plot, and then this quick look will be the actually solution that will incorporate all these variables in order to come up with the best solution. So these are result actually we are going to analyze these results, and then we will have 4 steps or 4 important step actually for our case is to focus on our PVT to see whether the gas lift injection is possible, and then we are going to see the match for our casing. Actually the model casing plot, and also the calculated one. So the well test data, and then find out the IPR parameters, and then tweak a little bit the reservoir pressure and other important variables in order to come up with a good match between the well test data and also the tubing response. So let's move to yes. Okay, for this tutorial number 3, we are going to actually as I said, there will be some data entry for our case. Okay, so for this one, we will going to use the same actually PVT data, and then we are going to enter the first step is to enter the well test data. So we are going to go for the matching. Okay, go for the matching, and then quick look. Okay. Okay, so this quick look, as you can see, there are cases in which, so include the data, flowing wellhead pressure to be 350. Okay, and then wellhead temperature 171 degree Fahrenheit, gross liquid rate 8,530. And then the water cut, same, is to be 80%. Measure total gas rate, 5.7 million scarf. Gas injection rate, 4 million scarf. Okay. Casing head pressure, 1,460. So about the gas injection data, the orifice diameter is 3264. Okay, 32. Just include 32. No, just because 64 is already actually embedded into the software, so 32 only. So the injection depth is 6,161. Okay, we are going to use the same, vertical flow correlation, PE2, and then dome pressure, we are going to change it to yes. As I said before, this needs to be changed to yes. Okay, and then the drafting parameter for orifice is okay. So in this case, we are going to okay, already all the data have been incorporated. Okay, click on okay, select the valve. Now we are going to include the valve data. Not done. Valve. Okay, for the valve, all the valves are casing sensitive. Okay, change all the valve to casing sensitive, and then we have 3 gas lift valve, as I said. So include the depth. First one, let's start with entering the data for the first gas lift valve. So the valve type is casing sensitive. The measured depth in feet will be 2,975. Port size will be 22. R value will be 0.038, and dome pressure will be 1,228. So let's move for the second one. Same, casing sensitive, 4,835, 22, 0.147, 0.147, not 187. R value 0.147, and then 1,197, 1197, and then for the third one, 5,885, 22.26, and then 1178. Okay, click on done. Okay. So let's move to the downhole data. Okay, for the downhole data, we need to include the actually the static pressure. So go for the measure depth, include it to be 8,000 feet, and then the static pressure to be 3,500. So this test was done during the time where actually the static pressure was 3,500. Now we are going to create actually the quick look plot. So in order to do that, click on done, and then click calculate. Okay, calculate. Okay, so calculation here will be done, and then click on the plot. Okay, so this is our plot. So let's enlarge the plot, please. Okay, now let's move to Zulkifli. Are you there? Field data. It's not going to be outside of this box, right? Whether the issue is from the model or whether the issue is from the well test data, right? So now what would be the you can see here we have three casing valve, and then you can see that here injection is not possible. Why the injection is not possible? You see shutting bottom hole pressure is 3,500. The flowing actually bottom hole pressure is about 2,100 something. So that's why we have a drawdown. But the flow is not going to reach to the surface because there is it's not possible to inject through this through the casing. And that's why this is one of the problem actually. So that's why in order to come up with the troubleshooting, I showed you in the slide number, yes, for the slide, we need to go for the first option, which is compare the calculated GOR and also the PVT model. Okay, so for this case, it's very important to know that to understand what you are dealing with. Okay, so what you are dealing with is that you have actually you have a plot, and then the result in this section is already compare the GOR. What would be the GOR? Here, as you can see, the GOR from the quick look data is the results is that your GOR free is 600 and the gas oil ratio is 400. Okay, so that's why you need to focus on the PVT and know any discrepancy between the actually PVT data and also the calculated results. But you can see that from our data, the bubble point pressure is 2,500, right? And also your reservoir pressure at the time of this test was 3,500. Okay, so as you can see, this shows that what is the type of your reservoir now? Not be 600. So this is the first case in which we are going to do some QC for our work. So we need to look for the PVT. We need to know our reservoir. What is the type of reservoir, and is it possible to have a GOR free of value of 6,000, but based on the fact and based on our case, our reservoir is undersaturated and there will be no free gas that can exist within the reservoir, So that's why we need to understand how we are going to calculate actually the theoretical produced associated gas rate. So when we calculate this associated produced gas rate, we need to minus this from our GOR. So that's why in order to calculate this, AGR or associated, produce or theoretical produced gas rate, we need to know our liquid rate, we need to know our GOR, we need to know our water cut. So I hope all of you know the formula. So we need to know our liquid rate. Our liquid rate is about 8,000 something multiplied to GOR, which is 400, and then multiplied by 1 minus our water cut, which is 0.8. So that's why the results will be about 0.682. So after we minus this 0.682 from 5.7, we need to come up with the value of our actually. So that's why let's move to so here I think all of you know that in this case the GOR free should be it's not true. So we know the reservoir pressure is 3,500 and the bubble point 2,500. So the well is highly undersaturated. So that's why we calculated back the associated actually produced gas to be about 0.6 million. And then we are going to calculate it back in our calculation. So click on finish. Okay, click on finish, and then okay, done. Okay, so now let's change the gas injection rate. So the total gas rate is about 4.7, right? So let's change it to when we minus this 5.7 from 0.6, it will be 5.0176. No, 5.7 is there. 5. Okay, great. So we have, the GR free. So that's why I told you this is all related to your liquid rate, water cut, and then so let's just do a water cut also. Change the water cut and see what would be the effect. Is there any effect? Change the water cut to maybe 70%. Okay, as you can see here, the GOR is already changed to, and then as you can see, there is a slight differences between your casing response, the calculated one, and also the measured one. Okay, so this is our first case. So change it to 80 again. And then do the calculation. So the first, that's why this is the first step. Let me show you. Okay, so this is the slide problem. Let's go for the next one. Okay, now you see, using actually the let's have the plot. Let's have the plot. Okay, so let's have the plot. So the second option was to, based on the presentation, find the deepest valve through which gas lift injection is possible by iteration. So as you can see in this case, using the casing pressure, the gas gradient is computed, and then this is labeled the casing and also tubing measured. So as you can see here, for our case, unfortunately, it says that the injection is not possible. Can you see that? You see how you can come up with the pressure actually of the annulus pressure. You see, all of you should know that the injection pressure in the annulus is the sum of the tubing pressure and also pressure drop across the valve. So what are the what you can see here is that visually the casing pressure should be higher than the tubing pressure. So, but in actual, can you zoom, Shank, on this case, on the intersection? Can you zoom in this intersection of the casing measured and also the tubing here? Yes, exactly. So as you can see, that the measured actually the tubing is higher than the casing pressure. So it's against our basis that says that actually the pressure of the casing annulus is the sum of the summation of tubing pressure and also the pressure loss across the valve. So the casing pressure should be higher in order to be able to inject. Okay, so in this case, you cannot inject because the casing pressure is lower than the tubing pressure, and of course there will be no injection. Okay, so how to solve this? To solve this issue, which is actually not being able to inject through the actually valve and into the tubing, is to change our our injection depth. So in order to do that, we need to make the injection depth actually change this injection depth accordingly. So for this case, let's click on finish. Okay. Click on finish and then done. Okay. Now, what is the injection depth here? 6161, right? So change it to 5885. So what we've done here is that we changed the injection depth from 6,000 to 5,885. And let's see what happens. Calculate. Calculate. And plot. Okay. So as you can see here, the message is disappeared. Okay. The message is disappeared, and then if you just zoom in to the intersection, as you can see here, the casing pressure, the measured one is above actually the tubing pressure. So this is logical. This shows that the gas is is able to be injected through the valve and into goes into the tubing and do its duty. So this is our third actually our third step. The second step. The first step is to change the to look for the PVT, do QC. The second is to look whether the injection is possible. The third, based on the presentation as I showed you, is to actually is to match the casing head pressure by iterating on the orifice size. Okay, So as you can see, the casing pressure, the theoretical casing pressure, in this case, is different than the measured one. So what can affect, okay, what can affect this, you know, these changes? Okay, what variables is directly related to change of you know, the pressure between this theoretical and the measured one? So let me go for it can be the surface choke, it can be the amount of gas, but in our case we are going to do iteration on the orifice, you know, the orifice size. So that's why for our case we will go and change the okay, can you click on finish? Okay, done. And then, okay, so you see, in our case, actually the calculated one was higher. The theoretical one was higher than the measured one. What does this mean? Means that the pressure drop, you know, the theoretical pressure drop was higher than the actually measured one. This indicates that the gas is passing through the actually small size actually orifice. So in order to reduce this pressure drop accordingly, we are going to increase the actually the port size. So that's why let's increase the port size from 32 to 54. Okay, wait a moment. I want to verify with all of you why we changed the orifice diameter. So that's why I'm going to refer to Walid. Walid, are you there?
Yes, doctor.
Okay, Walid, what is your inference about this changing the orifice? Why we are going to change this orifice?
Okay.
First of all, tell me what is orifice in gas lift? This is the operating valve, right? The lowest valve that gas will be injected, right?
Yes.
Okay. So now, the original size of the orifice was how much?
32.
32. Now it's 54, right?
Yeah.
Okay. Why we increase the size?
I'm not sure, doctor.
Okay, let's go for the tubing. You know why you know, lower tubing size is choose or higher tubing size is choose. Where do you use the lower tubing size? Lower tubing inside diameter, for example. Just to apply your knowledge in production and then just see and you know, to make it overlap with our case. So in this case, make it 32 again. Okay. Okay, make it 32 and do a calculation. Okay, Walid, can you locate the casing response? We need to validate our model. The model showing higher, but the measure showing lower means that there are some values that are actually not may not be correct. The first instance in gas lift design is to go for the variables that is directly related to the casing, actually calculation of the casing pressure. One of the variable is the orifice size. See, it's the orifice size. So as you can see, the pressure is higher, means that the pressure drop in the system is higher. So one of the important variables that affect this pressure drop is the orifice, right? So we need to increase or decrease. If we decrease, okay,
Well-
let's go back, Chen, finish. Make it 28. Then calculate back. Now what you can see, Walid,
Yeah, is the gap
the pressure is increased.
increase? Yeah.
So that means that this orifice is very important. Now let's decrease. We need to decrease now. We understand now that the trend is to decrease the orifice size in order to accommodate or in order to get a match actually for the casing theoretical. So let's go back and decrease the casing, the orifice size to be 54. Calculate back, calculate lots. Okay. So now what you can see here.
Now it's matched.
Okay, now is matched. Means that we already actually have a good match, and then casing is, you know, so the orifice is changed accordingly, and we have. So what would be the next problem for our case is that our tubing measured. Okay, thank you, Walid. Our tubing measured and tubing actually calculated also have the same actually issues. So now, what would affect actually the tubing response? Okay, so let me go for maybe yes. Okay. The question here, Ali, from you, let me come back to you.
Hey, doctor.
Do you have any doubt about the tubing size in your system? For example, the tubing size is 3.5 inches, okay? Do you think that the tubing size now needs to be changed to be 3 or 2.5 inches?
Doctor, if we decrease the diameter, that means the pressure will increase.
No, I know,
Yeah.
but the reason for changing the variables is that we don't know exactly what is going on. But for the tubing size, we know exactly the tubing size is 3.5 inches. So that's why if you go back, the downhole pressure, you see the downhole, you know, the changes in the tubing size is consistent. Means that from the downhole to the surface is consistent with the measured one. Means that actually if the tubing size was not correct, there might be a change from the injection depth. Means that there will be actually a change in pressure from injection depth to the surface. But in our case, we need to make sure that the variable that affect and the variables that have uncertainty. Remember, we are not going to change the tubing. This is not correct. We need to change the variables that have uncertainty in measurement. So 3.5 inches is already there. 3.5 inches is already there, means it's constant. We need to look for, this is not a drilling or completion, you know, this is a production. So means that what you have, you need to rely on what you have. So the tubing size is 3.5. Yes, tubing size can affect, but in our case, we need to make sure that we get a good match. In order to get a good match, we need to work with the uncertainty.
Okay, doctor.
Do you understand now?
Yeah, I got the point. I know the case now. So, doctor, if with this situation, so we have to make the drawdown higher, and then if we want to do this one, so we have to make the tubing head pressure less than now. So yeah, I think like this. So the drawdown will be
Okay.
higher, then will be much.
Okay, so tubing head pressure. So means that the first note. Go for the finish thing. And go for done. Okay, now the tubing head pressure is 350. You need to do what? Increase or decrease?
Decrease because we wanna increase the drawdown.
Okay, increase, make it 400. Okay, make it 500.
Become gap.
So you see, still this item also is not going to affect your case, because from the surface actually reading, you can read exactly from the choke. Normally in gas lift, you are not installing any surface choke. Okay, so that's why the wing valve reading the gauge, it's showing you actually the surface pressure. In our case, let's come back to our original original node tubing head pressure, which is 350. Okay. So in this case, what we are going to change is that we remember that the uncertainty in reading is about the IPR data. Okay. What we need to change is that we need to change those variables that we have doubt about them. Okay. One of the variables that affect this is actually our pressure, our productivity index. Okay. So that's why let's go for the actually downhole measurement. Okay, go for the matching another time, matching, quick look. Okay, and then go for the downhole. Okay, now what we are going to do is, because the measured one showing us lower actually pressure from the bottom hole, we are going to increase this, make it increase this to 3660, 110. No. This is for the measurement, static pressure below, static measurement. 3660. So now, Ali, do you understand why we increase this pressure?
Sorry, doctor.
Do you understand what is the reason that we increase this static pressure?
Doctor, you mean the BWF or the reservoir pressure?
The static pressure, the reservoir static pressure that we changed just now from 3,500 to 3,660. So what is the reason?
To increase the drawdown, doctor?
To decrease the drawdown?
No, increase the drawdown, increase.
Okay, so you see, the drawdown is the difference between your flowing and your static, right? So when your static is increased, means that your drawdown will decrease.
The drawdown will be decreased, yes, and then the PI will be increased.
Will be changed. Okay, so done. Click on done and then calculate. Then plot. So you can see that actually we also have here a good match. Okay, so it means that the takeaway actually from this is that you have a measured values and you have a theoretical value. You have a model. You need to make sure that the model is validated. In order to validate the model, you need to look for actually the variables that can that are not actually measured properly. For example, you measure the pressure for your field each year by year, So that's why this uncertainty is there, the productivity index and other things. So that's why you can do sensitivity on other variables and come up with actually this information actually about your case. So that's why you need to do sensitivity analysis on the unknown in your case. So the two possible solutions are the well productivity index and the reservoir pressure. Of course, well productivity index also related to the reservoir pressure. So reservoir pressure is the one that we are going to change. That based on this, we can have a good actually match. Of course, in order to have a better match, because you as a production engineer, you need to maintain the model. Means that every time a test is conducted, you need to look for the test, look if the test is looking good in terms of PVT, in terms of formation volume factor, in terms of viscosity. All the things needs to be checked and QC'd, and after that you need to make sure that the model is verified. Without verification and validation, the model, you cannot get actually future response and management decision for your well. And accordingly, if you want to create a system that is composed of several wells, for example, do gap analysis. For the gap, you need to have an individual wells. These individual wells needs to be actually showing exactly what is going on for each well. So that's why it's very important to confirm the finding with additional information, and that's why this case is very, very important. Okay, so I hope we conclude this